Hello everyone, I hope you're doing well. So in today's video, we'll be going through the 2020 physics exam part 2 of the short answer questions, where we'll pretty much go through questions 11 to questions 18. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 11. So an astronaut has left Earth and is traveling on a spaceship at this speed, directly towards the star known as Sirius, which is located 8.61 light years away from Earth as measured by the observer of the Earth. So let's draw a diagram. So basically, a nice diagram to kind of represent this. So you have, say this is Earth, so E. Let's say this is the planet S, which is Sirius. So basically, the distance is measured from the Earth's perspective is 8.61 light years, basically. And so we have a spaceship traveling from the Earth going to the Sirius, which travels at 0.800 C. Beautiful. So basically just looking at this diagram, we know that these astronauts are going to basically experience length contraction. So if they're going to see this distance here, very short. So this has to be here, your proper length. And so if this is proper length, this must be, these people must be in the Earth, must be measuring basically time dilation, and this here must be basically measuring your proper time. So your astronauts are measuring proper time. So this is how you can easily do that. So you've already determined what everything is, and it looks great. So an astronaut has left. So how long will the trip take according to the clock that the astronaut is carrying on the spaceship? So he's carrying the astronauts are going to be measuring the proper time. So we know proper time is what? So proper time is your time dilated over your Lorentz factor. So, okay, so how do we calculate your time dilated basically? To calculate the time dilated, we know the distance that's measured by the Earth, and we also we know the speed is going to be the same for all observers because that's Einstein's second postulate. So we can easily calculate. Okay, so basically your time that's going to be dilated is L0 over your velocity. But L0 is in 8.61 light years away from Earth. I mean, this is kind of stupid because they could have told. I've done an exam. I think it was the 2018 Northern Hemisphere. That basically had light years as a measurement for distance, but it told you how much each was in meters. This is how you actually determine it. So light years, I believe its meaning by light years is that, so you have, so 8.61. Okay, let's convert it to meters. So 8.61 light years. It means light means the speed of light. So 3.0 times 10 to the power 8 times years. So years, there's 365 days in a year. And basically, so we know there's 365. Each day has 24 hours, and you multiply by 60 and 60 again to get it into seconds. And so that here is the conversion to meters. And I think it's kind of rubbish, to be honest, because it's a lot of work. Light years. To convert light years. And it's, so that, and your velocity is basically just 0.800 times 3.0 times 10 to the power of 8. So basically that will give me 0 times 10 to the power 8. 365 times 24 times 60 times 60. 0.8 times 3.0 times 10 to the power 8. It gives me basically the time that's dilated. Basically 3.4 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8 seconds. So, using our formula, so proper time is basically that divided by your gamma, which is 1.67. So that gives me what? 1.67. That gives me the time that's dilated basically now. But that's in seconds, so we want it in years. So that's going to be 2.0. times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8. 8 seconds, and make sure just get it in years. So basically divided by 60, divided again by 60, divided by 24, and divided by 365. basically that gives me 6.44 years. I mean, that is such a long question for 2 marks. Especially they didn't tell you that light years, how to convert light years to meters. So, I mean, just, yeah, it's a kind of a stupid question, to be honest. I don't like that one. 8.61 light years away from Earth. Wow. Is the trip measured by the astronaut in part A proper time? Explain your reasoning. Yes, it is. It is proper time that the astronauts are measuring. And so we need to explain why. Well, easily. So because the 2 events, basically going from the Earth to the planet Ceres, occurred at the same location in space, which is basically the spacecraft. So the astronaut remains stationary in that frame of reference, basically. So that has to be its proper time, basically. They're going to be measuring proper time. Perfect. So that's what we need to say. I mean, just define proper time. Like, there we, yep. So yes. So the astronaut. So we can say that the astronaut measures proper time. Because 2 events occur at the same location in space and remain stationary in the astronauts. So yeah, you didn't need to say frame of reference. Frame of reference. I mean, that is it. I think that, yeah, so you've basically said, yes, it is. That should give you a mark. And you've just basically defined what proper time is. Easy. That looks good. Yeah, did not like this one. I'm not too sure if that's correct, so I need to double check that. But I think it's a garbage question. Question 12. In young double slits interference experiment, laser light is incident on 2 slits, S1 and S2, that are so they're apart at that distance. Rays from the slit is 2 meters from the slits to produce an interference pattern. Point C is the center of pattern. Beautiful. Figure B shows the pattern obtained on the screen. Okay, so that looks good. There's a bright fringe at point P on the screen. Explain how basically this bright fringe is formed. Easy. So if it's a bright fringe, I mean, look, it doesn't look bright here, but it is actually bright. It's just because it's the I've kind of used the black and white color paper, so on my iPad. So basically this here, whatever you see, these are black. The white are black, and basically the black, yeah, so it's basically black. So what I'm going to do is, the way that I would check is by seeing the wavelength. Because, okay, if I know that's going to be 1, 1, 2, 2, 3, 3, 4, 4. I know that n is equal to 4. It's the 4th bright band, basically, from the center. And so we know that path difference is basically n pi. So, n, what am I saying, n pi, but n wavelength. So this means that it's 4 times your wavelength. Your path difference is 4 times the wavelength, meaning that constructive interference occurs at point B, and that's why there is a bright band. Quite easy. That's it. Yeah. So because it's 4 times your wavelength, basically. And so that's why constructive interference happens. So basically all you need to say, because it's 2 marks, it's very easy to get those marks. You just need to basically say, so path difference is 4 times lambda, hence constructive interference occurs at P. That is it. Nice. So path difference is 4 pi. That's, I think, yeah, that's all you need. You don't need to go deeper. You always talk about the path difference. Yep, so it's 4 pi, so it's an integer. Multiple, so hence constructive interference occurs at point P. Beautiful. Alright, that looks good. The distance from the central bright fringe at point C to the bright fringe at point P is that. So they've told us, okay. Calculate the wavelength of the laser light. Alright. Let's think about this. So remember the black one. So basically we have the distance from here to P. The center of P, basically. Which is here. So we have that distance from the center, from C to P, which is that distance over here. So remember, these here are actually white. These are white and these are dark. So it's just the opposite because I'm using black and white. So let's think about it. So I know that distance. All I need to basically, because I have everything here, I've got the distance, this distance, and basically that change. I need to just calculate that change in X because I've been given the distance between the slit, the distance between the actual screen and the slits. And yeah, so basically we need to just find that change in X, which gives me that it's lambda L over D. We know this D, which is the distance between the slits, the L between the screen, and we just need to get change in X to get the wavelength. That's not too bad because what we can do is, if we half this distance, it will give us the distance, basically this distance over here. And if we half it again, so basically here, if we half it again, we get this distance now. So basically we've quartered that. Have a look at this. Now this is actually your change in X because it's the distance between the second antinode. So if this is an antinode here, this is the second antinode. That's our change in X. So basically, all we had to do was divide this by 4. So basically your change in X is 1.26 times 10 to the power of -2 divided by 4. And that's going to give me what? So 1.26 times 10 to the -2 divided by 4. That gives me 0.00315 is equal to lambda. So what's the length between the screen? So 2 times your distance between the slits, which is 4 times 10 to the -2, if I'm not mistaken. -4, sorry. There we go. So 4 times 10 to the -4. Beautiful. So that's going to give me what? -4 divided by 2. And then I want to get in nanometers. So I'm going to times 10 to the power 9. I get basically 630. Beautiful. Yeah. Question 13. Let's have a try at this. So a 0.8 meter long guitar string is set vibrating at a frequency of 250 hertz. The standing wave envelope creating the guitar string is shown. So, okay, so this is what happens. Calculate the speed of the wavelength in the guitar. Now, okay, that's easy because if we know that n equals 1, this is the fundamental harmonic, basically. So if we want to calculate speed, what is the speed? How do you calculate that? So looking at my formulas, because I've given the frequency. This is at fixed 2 ends. This is at fixed end. So I know that basically frequency is basically, what am I doing? So frequency is NV over 2L. So basically 2LF divided by your N is going to give you your velocity. So your velocity is just 2 times your length of the wire times your frequency, which is 250 hertz, all being divided by your basic harmonic, which is 1. Your N equals 1. 0.8, 250. Oh, what happened there? What is it saying? Oh, okay, so 0.8, 250. That gives me 400 meters per second. Beautiful. The frequency of the vibration in the guitar string is tripled. All right, if you triple it, okay, on the guitar string, draw the shapes of the standing wave. So if you triple it, you get n equals 3. Basically, the way you this is the way I determine what value of n we are using. It's just, if you look at this here, if it's one full, if you get like, let's say, 2 of them, that's 1 and that's 2. That's how I calculate the values of n. Now we have n equals 3 basically, so we just need to, so it's going to be 1, 2, I mean, that's not nice, but something like that. Duplicate that. Like that. Duplicate that. And there we go. Something like this, basically. And, of course, the opposite way. Duplicate this. So you can see now that's in when, basically, oops, there we go. That's when n equals 3 because we have 3 of these loops. That's the way you do it. 3 of these loops. Beautiful. Done. All good. Question 14. Figure 13 shows a representation of the electromagnetic wave. Correctly label figure 13 using the following symbols. So we need to label the electrical field, magnetic field, speed of light, and the wavelength. Beautiful. So the speed of light is basically going this way. It's going at this speed of light at this way, basically. The wavelength is what is the distance for one actual wave? What's the distance of basically a wave? So from here, so you can see that one. So for one full wave, you can see that's the distance basically, and so I'm going to call that lambda. So from here to here, you can see that because that's one wave basically, one cycle. All right. So we got that, and we also need to really electrical field and magnetic field. You don't know which one it is, so it could be any of them. So basically, just I would say, this one over here is my electrical field, and this one over here is my magnetic field, and that's it basically. I mean, if you have it the other way, you still get the mark, because they haven't been precise on which one is. Beautiful. Question 15. The metal surface in a photoelectrical cell is exposed to a light of a single frequency and intensity in the apparatus shown. The voltage of the battery can be varied in value and reversed in the direction. All right. The graph of the photocurrent versus voltage for one particular experiment is shown in figure 15. On figure 15, draw the trace that would result for another experiment using light of the same frequency, okay, but with the triple the intensity. So remember, frequency affects the stopping voltage. Intensity affects the photocurrent. So if you triple the intensity, you're basically tripling this. So if let's say estimate, how would this graph look? So basically this here is, I would say estimate as to be 1.5. And now just triple it basically. So what's 1.5 times 3? It's 4.5. So it's going to be 1, 2, 3, 4. It's around here basically. So basically it's going to have that. And it's going to have that distance because it's tripled. And now it's just going to, and basically it's going to have that same stopping voltage because you haven't done anything to the frequency. Remember? That's it. So, beautiful. That looks good. What is the name given to the point labeled A? This is your stopping voltage. Beautiful. Stopping voltage. Why does the photocurrent fall to 0 at the point labeled A? Why? So like basically just define, because it's one mark, basically define what the stopping voltage is. So the stopping voltage is basically, so if you have, so basically this is your negative charge and this is your positively charged. And what basically happens is well, no, this is the opposite, sorry. What am I saying? So basically, this is basically initially negative and this is positive basically, this charge. So basically electrons are straight away going to go what am I doing? No, what am I doing? No, I fully made the biggest mistake. I don't know what I'm doing. Am I tired or something? So this is positive. Yeah, this is positive. This is positive. This is negative. So what happens is that electrons, when they let go here, when they release basically, they go to this positive electrode basically, and they pass through basically through the cell. And yeah, but what the stopping voltage is because you can vary it, it's a variable voltage, you can start varying it as you decrease the voltage. And why is it negative? But it's negative because you change the polarities. So that's going to be now negative, and the other part is going to be positive. So now what happens? So electrons are releasing, but guess what's happening? This is negative and this is positive. So the electrons are going to go the opposite way because they're going to be repelled by that negative. So it's basically a voltage that basically does not allow any photoelectrons to reach this negative electrode, basically. That's what it does. It's just a voltage. Where the photocurrent, as you can see from here, where the photocurrent is 0. It just basically, it's a voltage that stops all the photoelectrons, even the strongest energy ones, even those with the highest energy, from reaching the negative electrodes. Basically, hence no photocurrent is produced. I hope that makes sense, yeah. So let's write that down. So voltage. So we can say voltage that stops, basically that stops all photoelectrons from reaching the negative electrode. There we go. And I think that's it. I mean, you don't have to go in detail. It's only 1 mark, so I hope that makes sense. Question 16. A beam of electrons traveling at this speed illuminates a crystal, producing a diffraction pattern as shown in this. Take the mass of an electron to be this. Ignore relativistic effects. Calculate the kinetic energy of 1 electron. Beautiful. And so we want it in electrovolts. So we know that kinetic energy is half mv squared. Where half, what's our mass of an, so it's 9.1 times 10 to the negative 31. What's our velocity of an electron? It's 1.72 times 10 to the power of 5 being all squared. Alright, so that's 0.5. 9.1 times 10 to the negative 31. 1.72 times 10 to the power of 5 squared. I want to just double check if everything looks good. That looks all good. So that gives me basically 1.346 times 10 to the power of negative 20 joules. And make sure to get it in electrovolts. That's the unit. So what we just have to do basically is divide that value by 1.6 times 10 to the negative 19. And so that gives me basically just 0.084. Done. B. The electron beam is now replaced with an X-ray beam. The resulting diffraction pattern has the same spacing as, that produced by an electron beam. So, yep, they have the same wavelength. Calculate the energy of 1 X-ray photon show working out. Beautiful. So, let's do that. So, I know the kinetic energy, but I want it in joules, basically. We calculated it, which was that. So, I'm just going to get it again. 1.6 times 10 to the negative. So, it was basically, this was my kinetic energy. I know that momentum and wavelength are the same for both X-rays, and if we want to produce, of course, the same pattern, the X-rays and the electrons are going to have the same wavelength and momentum. So I'm looking at my formula sheet. What formula will give me momentum right now? Okay, so I can relate that kinetic energy is basically the square root of 2 times your kinetic energy, 2m times kinetic energy. So basically, your momentum is 2. Your mass of an electron is 9.6 times 10 to the negative 31. Your kinetic energy is 1.346 times 10 to the negative 20. So what's that going to be giving me? 2 times 9.1 10 to the 31. That gives me 1.5652 times 10 to the negative 25 kilogram per meter second. Beautiful. So we got our momentum, and now we just want to calculate the energy of a photon. So if we have a calculate energy, so we know that energy of a photon can be calculated by P times C. So your momentum times your speed of light. So that's going to be basically 1.5652 times 10 to the negative 25 times 3.08 times 10 to the power of 8. So overall, I got my energy of a X-ray, but I want it in, make sure this is in joules, so we want to make an electrovolt. So write it here, 4.695, 6 times 10 to the power of negative 17 joules. So make sure you just divide it by 1.6 times 10 to the negative 19. Doing that, I get basically 293. Beautiful. Question 17. Figure 17 shows the emission of spectrum for helium gas. Alright. What spectral line indicates the photon with the lowest energy? So the lowest energy means the lowest frequency. If we have low frequency, it means that we have high wavelength. So which one has the highest wavelength? Basically, looking at this, the one that has the biggest wavelength is this here. This part, 668. That's the highest wavelength from all of them. So 668 nanometers. Calculate the frequency of the photon emitted at 588 nanometer line. Show working out. So we want to calculate the frequency of this photon. So let's have a look at my formula sheet. Beautiful. So I know that velocity is of course frequency times your wavelength, because we're given the wavelength. It means that frequency is just your velocity over your wavelength. So 3.0 times 10 to the power of 8, all being divided by your wavelength, which is 588 times 10 to the negative 9. Beautiful. That looks correct. So 3.0 times 10 to the power of 8, 588 times 10 to the negative 9. That gives you, wow, it's a big number. So 5.10 times 10 to the power of 14 hertz. Does that look good? Yes, looks good. Explain why only certain wavelengths and therefore certain energies are present in the helium spectrum. This is very easy. This is like the most kind of common questions you'll get in exams. So it's just basically, you just need to basically explain why there is these specific, values of wavelengths. Now, all you have to basically explain is these. You just need to explain why electrons exist in discrete energy levels, and how basically electrons basically go from high level states, like your high energy states, and they go through low energy state. When they kind of transition to that low energy state, they kind of emit photons with discrete amount of energy. And so if they basically emit a discrete amount of energy, this, because energy is related to wavelength, it means that also wavelength is emitted in discrete amounts. And that's why we have only discrete amount of wavelengths, so peaks here. That one, yeah. It's not all of them, basically. That's all you need to kind of explain, yeah. I've kind of written, yeah, these are quite fun and easy because every year they kind of repeat. So it's just have these in your summary sheet to straight away, yeah, smash them out. So we're going to say, let's say electrons. We said, so electrons exist. So electrons exist in discrete energy levels. When an electron transitions from a high state, from a high state to a low energy state, it can only emit discrete amounts of energy. So hence only certain wavelengths are present. That's it. That's why we have certain wavelengths. That's it. Easy. Question 18, so the last question. So so that's the last question. Alright, so question 18, let's smash through this. Students are modeling the effect of the resistance of electrical cable R on the transmission of electrical power. They model the cables using the circuit shown in figure 18. Okay. So we have power, resistance of electrical cable, and the resistance of the globe. The 24 volt DC power supply models the main power. Describe the effect of increasing the resistance of the electrical cable, so R, on the brightness of the constant resistance globe R, the big R. Okay, if you increase this resistance, this is a big problem. It's a no-no because there will be much power loss in these electrical cables. Remember, power loss is I squared over R. So if you increase this resistance for this, it means that there's power loss in this, there will be higher power loss in this cables, and so there will be less energy to be able to be delivered to that globe. And so if there's less power, it means basically the brightness is going to be dimmer and lower. So that's not a good way to kind of do that. Yeah, I think that's all we need to explain. Describe the effect of increasing the resistance on the brightness. The brightness is going to decrease, like we just said, and because you're basically increase your power loss in those electrical cables, and only small amount of energy will be given to the globe. Oh, power. Yep. So I'm just going to say the brightness will decrease. That's the first mark. And you just need to explain why. So an increasing resistance an increase in resistance increases power loss in the electrical cables. Hence, only little power will be delivered to the globe. Beautiful. And that's it, yeah. Next question. The students investigate the effects of changing R by measuring the current in the electrical cables for a range of values. Their results are shown. So, okay, we're given the resistance of R. Currents in the cable were given, and yeah, so we're now just calculating 1 over I. So, yeah, let's do that. We're given I, it's 1 over that. So, 1 over 2.4. That's going to give me 0.42. Next one's 1 over 2. This is 0.50. 1 over 1.7. 0.59 basically. 1 over 1.5. 0.67. And 1 over 1.3. Yes, there's 0.77. Beautiful. Identify the dependent and independent variables in this experiment. So, okay, your independent variable is the variable that you pretty much play around, or the variable that you can affect. Independent variable is what? So what if, yes, it's your resistance, because the students investigate the effect of changing. They can change that resistance. And what are they measuring? The current. So your dependent variable is the current, because that's what we're trying to measure. So, absolutely. So independent variable is R, basically. R, which is your resistance of cable. Your dependent variable is your current. Yep, so current. That's it. Okay. Done. So, see, to analyze the data, the students use the following equation to calculate the resistance of the cable for the circuit. That's the formula. They calculate that. Show that the equation is true for the circuit shown in figure 18. Show it working out. So, let's do that. So what we're trying to do is basically make a formula that calculates the resistance of little r. So the first thing that basically, this is a basic circuit. You should basically know how to do this. This is like year 11, basically, physics. So what you need to do is basically, you need to find the total resistance. Your total resistance, or RT, which is basically, because it's a series circuit, you just add these resistance. R plus your big R. So we found our total resistance. We've given the voltage, basically, and current is I that passes through it. So what we're going to do is basically, we're going to use Ohm's law, where voltage is current times your resistance. So our voltage is 24. Our current is what? I, basically, little I. And your resistance is your total resistance, which are these over here. So basically, we've written it in a nice formula. And so now what we're going to do is basically, we're trying to solve for, so I is the subject. Let's make sure it's I subject. So what I'm going to do is expand this out. So 24 Ri plus Ri. So 24 minus Ri is equal to Ri. Divide both sides by I to get rid of that I here. And so we're left with basically 24, because you can divide that by I and divide that by I. That'll be 24I minus, those will cancel out, so minus R. Because these I's will cancel out, basically. So we're left with, the formula. That's the proof of the formula. So I'm going to basically copy this whole thing here. I'm going to bring it down to where it is, because I'm not going to rewrite it. That's basically the proof. Just wanted to see it. And yeah, so, okay, I'm going to put this here and take this here, put it right over here, and put that there. That's where the formula comes, basically. Calculate the values of 1 over I and write them in the space provided in the column of table 1. Oh, we've already done that. That's perfect. So E And yeah, that's the last page. Let's smash through it. Plot the graph of R, okay, on the y-axis against 1 over I, on the x-axis on the grid provided below. All right. Choose an appropriate scale and numbers for the x-axis. So they haven't done the scales for the x-axis. Draw a straight line of best fit through the plotted points. Include uncertainty bars for the x direction, which is 0.0 that. Uncertainty bars in the y direction are not required. And then use a straight line of best fit to find the y value of the constant resistance globe R. Give your reasoning. All right, so let's plot those points first. All right, so what I'm going to do is basically, I need to find the scale. So if that's going by 0.4 and they go to basically 0.7, I think what I'm going to do, the best I would say is maybe 0.05 each or 0.01. So if I basically did every two, this point, 0.01, that'll be 1, 2, 3, 4, 5, 6, 7, and 8, 9. Yep, that's actually good. So if I do basically all these 0.1, that's 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, basically. These are those. And we've already given the values, the axis for these, so that's good. Now let's plot. All right, let's see what we're first plotting. Okay, so we're plotting 0.42 first, so the line 0.42, which is, yep, 0.42. So 0.42, that's 0.45, 0.2, it's around right over here, basically. Approximately there. And it's 2.4. So basically that's going to be 1, 2, around, so 1, 2, 3, around here. So I'm going to just draw a little cross there. There we go. Next one. Oh, what am I? Yeah, so 2.4. Perfect. So 0.5, which is here basically. So 0.5 is going to be 3.6. So 3.6. So, alright, so it's going to be 1, 2, 3, 3. So sorry, 1, 2, 3. That's 4, so it's 3.6 around here. Done. Next one is basically 0.59, so approximately 0.6, so right here. And so 6.4. So that's 5, 6, 7, so 6.4, it's around here. Oops. 6, 7, so right here. Let me double check actually. So 6.4. 5, 6, 7, so it's, yep, that looks good. Perfect. So next one, 0.67. 5, halfway there, so it's around here. And 7.6. 5, 6, 7, 8, so it's around here. This is taking longer than expected, but yeah. Next one is 0.77. So let's draw that line. That's halfway there, so it's around there. That's 0.77 and 10.4 basically. 10, 11, 10.4, it's around here. Beautiful, that's it. So let's include those uncertainty bars too. So the uncertainty is 0.02. So what I'm going to do is basically look at this and say, okay, if I know that each of these squares, so if I just draw like a dot here, and I know that each of these squares is basically, 0.05 here, and we want 0, so it's absolutely like around here for each of these square. Because halfway through here is 0.25, and so it's a little bit there, so perfect. So I'm going to take that and I'm going to copy and duplicate and put it everywhere. So that, duplicate, and that point, duplicate, 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 okay. Perfect, and that's it. Just a quick way, and let's draw a line of best fit, basically, a straight line that passes through it. Something like this. A line that basically passes through this whole thing. Is it? So it doesn't pass around here. So if I draw like that, like there, around there, that passes through, yep, passes through that one. Yep, that looks good. So it passes through most of them. So we traced the appropriate unit, drawn a straight line, included all those uncertainty bars, and yeah, now use the straight line of best fit to find the value of the constant resistance globe R. Okay, so let's try using the gradient. So if I calculate the gradient, which is basically R over your x-axis, which is 1 over I, which is basically going to give us Ri, that's going to be our gradient. How let's see how we can use that gradient to help us calculate big R, this one. So if I multiply both sides by Ri, that gives me 24 minus Ri. So I can get that there, but no, I have I there. That's the problem. So I can't use the gradient, basically. Oh. Okay. Let's find another way. So, okay. Okay, I see the pattern here. So have a look at this. This is our straight line equation because R, imagine R is our Y. Think of it there. It's our Y values. This is our X. 1 over I is, just imagine it as X-axis, our X value. So imagine it's 24 times 1 over I. 1 over, think of it as our X value. So think of it as a straight line, basically. That's X minus R. So basically, what is R? I, for this graph, is your y-intercept. So imagine like a y equals mx plus c. This here, that value is actually our your y value of our, resistance. So yeah. So basically all we have to do, because it's our y value, to calculate the resistance is just finding the y value using the graph. So basically let's continue off this graph to get a nice, looking at it like, let me just draw it like that. Something like, there we go. Approximately, that looks good. So what's our y value? So from this, I can see that the y value is, so that's -5, -6, -7, around -7.5, basically. Yeah, -7.5. So 7.5. Make sure don't put negative because it's going to be a negative answer. It tells you it's negative. So, but it's a resistance, so negative. So it's basically 7.5 ohms. The answers can vary because maybe some students will get maybe 7 or maybe 8. So yeah, it has to be around those range. So you still get the full mark. And we just need to explain, give you a reasoning why. So R is the y-intercept of the graph. And I think that's enough. I'm not going to lie. One mark for your answer and the other mark just explaining how you got R. Which, yeah, I thought the gradient, because normally all these questions tend to use gradient to kind of get their questions, but to get the answer. But yeah, this one didn't really work. Perfect. I hope this paper, I hope that these questions are basically all right. I'm going to try to check these solutions. So yeah, I hope you guys enjoyed this video. Please make sure to like and subscribe and share this video with friends. I hope it helped you a lot. And yeah, guys, make sure you take care of yourselves. Bye-bye.